having discussed zeta potential and the importance of zeta potential measurement in some of the problems, we will look at electrokinetics further. Electrokinetics implies a combined effect of motion and electrical phenomena, and such phenomena can be observed whenever you have a heterogeneous fluid that is, in case you have a particle filled fluids, and if these particles are charged, then you will have an electrical double layer associated with it. So, whenever you have systems like this, the electrokinetics effects become important, and such phenomena is of interest because that will help, these phenomena will help us to study charge stabilized colloids or system in which the colloidal particles are charged. Before we talk about electrokinetic phenomena in colloidal system, I would like to introduce electrokinetic phenomena from a concept that you may already be familiar with. If you look at electroplating process, in which what is done is an external electric field is applied to a solution which contain metal ions. The schematic is given here. So, there is an anode and a cathode, okay, and you can imagine that there is the bath of electrolyte which contain like say metal salts, okay, and whenever an electric field is applied, what happens is that there is a migration of ions, and then this metal ions may get deposited on the electrode, so that you can get a metal coating on substrates. Okay, this is one of the commonly used technique called electroplating, what you see in electroplating is that there is a migration of ion. Positive ions migrate towards the cathode and the negative ions migrate towards anode, so similar to migration of ion, if you have positively charged particles or negatively charged particles, there will be a migration of colloidal particles similar to the migration of the ions that we have discussed. Therefore, the electroplating process is an example of a phenomena where electrokinetics is observed. So, there are several examples of electrokinetic phenomena that we are going to discuss. We will mostly focus upon the electrophoresis. However, there are also other techniques called electro osmosis, streaming potential, sedimentation potential, which are also important in the context of studying charged surfaces. Mainly this four electrokinetic phenomena can be subdivided into two categories. One category where charged surface is stationary and the fluid is made to move around, fluid around it is made to move. Okay. So, therefore, you could have a case where I have a charged particle, for example, then there is fluid around it. So, if this is a fluid, okay, so in a class of technique, the charged particle is stationary or the charged surface is stationary. However, the fluid that is surrounding the charged surface is made to move. In other class of technique, the charged surface is made to move while the fluid surrounding it is stationary. Okay, we will discuss some of these techniques not in great detail, but just to give an idea of what these methods are. In electrophoresis, electrophoresis is very similar to what we saw in the case of electroplating. Electrophoresis refers to a movement of a charged particle relative to a stationary fluid due to the application of an electric field or due to the application of an external electric field. Okay. So, you have particles in a fluid, there is an anode and a cathode, and you have a charged particle that is depicted here, and there is an electrical double layer that is associated with the charged particle, and whenever you apply an electric field, okay, what happens is that the particle moves. Okay. This phenomena is what is called as electrophoresis. So, this is a video of an electrophoresis which is observed. So, what you are looking at is a a video where the circular dots that you see here, these are all the particles, and you will notice that the particles are moving in a particular direction until some time. Okay, let me just play the video again. So, the particles are moving in this direction initially. After a while, you will see that the particles start moving in the opposite direction, that is, now they are moving in the opposite direction, right. So, now this is a case where you have charged particles which are in between two electrodes, and what is applied is an AC electric field, and because of the alternating polarity, you will see that the particles move in one direction during one cycle, and they move in the opposite direction in the other cycle. And you could of course have a case where what is called as a DC electrophoresis, when you will see that the charged particles, depending upon whether positively charged or negatively charged, they will start moving towards one of the electrodes as well. So, okay. So, this is an example where there are charged particles in a fluid, and you set the particle into motion by applying an external electric field. Now, another class of technique called Electro Osmosis. There are two schematics here, okay, and so you could think about this schematic as a case where you have a pore, and say that the surface of the pore is charged. In this case, it is negatively charged, and what is contained between the charged surface is an electrolyte solution. Okay. And now what you could do is that you could apply an electric field, okay, which can be generated by having two electrodes and supply and connecting the two electrodes to an external supply. Okay. So, now when you apply electric field, what happens is that the electrolyte solution that is between the two charged surfaces is set into motion. So, electro osmosis refers to the movement of the electrolyte surrounding a charged surface, and the movement of the electrolyte is achieved by the application of an electric field. However, the charged surface is stationary. Therefore, the electrolyte solution moves with the charged surface being stationary. Therefore, there is a relative motion that is set in because of the applied electric field. The pressure that is necessary to balance the flow that is set up because of the applied external electric field is what is called as electro osmotic flow, and this pressure, which is called the electro osmotic pressure, can be easily measured, and one could correlate the electro osmotic pressure to the charge of the surfaces that we would like to investigate. So, therefore, in this technique, what is set into motion is the electrolyte, and the motion is set by an applied external field, and what is measured is the osmotic pressure, and that can be related to the charge of the stationary surface. On the contrary, in what is called as a streaming potential, what is done is the electrolyte is made to move by applying a pressure gradient. We know that whenever you have a charged surface, and if there is electrolyte which is in between these two charged surfaces, I can set up a fluid motion by applying a pressure gradient. Okay. And because of the fact that now you have charged species in the electrolyte, their motion is going to induce an electric field, okay, and that electric field is what is measured in streaming potential. The effective electric field that is developed is what is called as streaming potential. So, the difference between the osmotic electro osmosis and the and the streaming potential is essentially that the phenomena are similar, that is you have stationary charged surfaces in both the cases, and what is moving is the electrolyte. However, in the electro osmosis, the electrolyte is made to move by applying an external electric field. However, in the case of streaming potential, the electrolyte is set into motion by applying a pressure gradient. Okay. The last of the electrokinetic technique is what is called as sedimentation potential. So, we know that if you have a system that contains particles, and these particles can sediment to the bottom of the container either because of gravity or centrifugal force. Okay. So, if the fluid density is like say rho fluid, and if the particle density is rho p, so we know that rho p minus rho f is an important parameter which will dictate whether there is going to be sedimentation of particles, which is driven by gravity or centrifugal force. If there is a large difference between the density of the particle and the fluid, we can expect that the gravity settling would be prominent. However, if the delta rho or the density difference is small, then one could make the particle settle by the application of an external field. Now, if these particles are charged, okay, let us consider these particles are positively charged. Now, because of the fact that you have charged particles now, and the motion of these charged particles can set up an electric field. Okay. So, now if you look at individual particles, so we know that I have a particle that is charged. Now, every charged particles would have an electrical double layer associated with it. Okay. So, we know that there is going to be counter ions in solution, okay, and more counter ions as we go away from the surface, and of course, there are going to be co-ions as well. Now, because of so when the particles are stationary, this electrical double layer around a charged particles is symmetric. However, when the particles move because of the gravity, there is going to be a distortion of the electrical double layers. That means, if they are moving in a particular direction, okay, so if they are moving in this particular direction, you will see that the charged particle is here. Now, the electrical double layer around it is going to be somewhat distorted, okay, with more counter ions in one region versus the other. So, because of which the system of the colloidal particle and the associated double layer looks more like a dipole. Okay. So, whenever you have charged particles settling, you can imagine that instead of a colloidal particle, every particle and electrical double layer combination can be imagined like a dipole, and the summation of all these dipoles will lead to an effective electric field, and that effective electric field that is developed is what is called as sedimentation potential. Therefore, if you essentially take two regions, for example, region 1 here and region 2 here, and if you measure the potential difference, there is going to be a potential difference that is developed that will depend on the concentration of the particle that you have, the surface charge on the particle, and a lot of other parameters, and this potential difference can be measured, and that potential is what is called as a sedimentation potential. Therefore, so one could measure sedimentation potential, and of course, this can again be related to the charge of the particle or the zeta potential as well. Okay. So, now we will look at electrophoresis in a little bit more detail. So, before we talk about electrophoresis of colloidal scale particles, what we will do is we will consider a simple case of electrophoresis of an ion in an electric field. So, what you have is a positively charged ion, it could be ion with any polarity. So, there is an anode and there is a cathode. Now, an isolated electron, okay, in a or an isolated ion in an electric field experiences a force that is directed towards the oppositely charged electrode, right. So, if you have a positive charge, it will move towards cathode, and if you have a negative charge, it will move towards anode. Okay. So, that force essentially is proportional to the strength of the electric field that is applied. Okay. The strength of the electric field times the Q, that is the charge of the isolated ion, essentially gives you the force that the isolated ion is experiencing. Okay. So, initially the ion could be stationary or it could be moving about because of the Brownian motion. However, once the external field is applied, it will move with this force towards the oppositely charged electrode. Okay. So, when the electric field is applied, so first the ion is going to accelerate, that means there is going to be a sudden increase in the velocity of the isolated ion. However, this initial increase is going to die down with time, that is because you have an there is an opposing force that comes into picture. So, because of the fact that whenever there is a relative motion between the particle and the fluid, right. So, this ion is set into motion. Now, whenever there is a relative motion between the ion and the fluid that is surrounding it, there is going to be a viscous force that comes into picture, and this viscous force is going to oppose the motion of the isolated ion, and this force F viscous is given by some friction factor F times the velocity with which the isolated ion is moving, and soon an equilibrium will be set up between the two forces that are acting on the isolated ion, and that is established when the two forces that are acting on the species are equal. Therefore, we could equate the electrical force that is generated because of the applied electric field and the viscous force, that is F times V, that is set up because of the drag that the moving ion experiences in the fluid. Okay. So, therefore, we could obtain an expression for the velocity with which the fluid is moving in the we can obtain an expression for the velocity with which the ion is moving in the fluid, and that is given by Q times E divided by F. Now, because we are dealing with species that are very small, right, the dimensions of these species are going to be of the order of sub nanometer. Okay. So, whenever you have such small species, if you calculate the particle Reynolds number, which goes as diameter of the ion that we are considering times the velocity with which they are moving times the fluid density divided by viscosity of the fluid, because of the fact that the dimension of the species are very small, this Reynolds number, if you calculate, it will be much less than 1. Okay. So, under such condition, these you can refer to this as a low Reynolds number flows. Therefore, we could use Stokes law and therefore, the friction factor F, okay, can be replaced with 6 pi eta times Rs. Okay, this essentially comes from the F Stokes, right, the Stokes law for low Reynolds number force. Therefore, in V is equal to Q E divided by F, we could replace F with Q E divided by 6 pi eta into Rs. Okay. So, therefore, we end up with an expression which is the velocity with which the particles are moving, with which the ions are moving in the field, goes as Q times E divided by 6 pi eta times Rs. So, I can rearrange this expression further. I can write this as V by E is equal to Q divided by 6 pi eta into Rs. Okay. And this quantity V by E is what is called as electrophoretic mobility, that is the velocity with which the isolated ion is moving in the presence of an applied electric field of a given strength, okay, is what is called as mobility or the electrophoretic mobility. And for simple ions, the typical value of electrophoretic mobility would be of the order of 10 power minus 8 to 10 power minus 9 meter second inverse divided by Joules per meter. So, if you look at this expression, the E, that is the electric field that is applied, it is measured in terms of Joules per meter. Okay. So, that is because whenever one does electrophoretic experiments, typically you have an anode and a cathode, which are anode and a cathode, which are separated by some distance, some known distance, okay, like say d, and so you can manipulate the electric field that is applied by considering different distance between the electrodes. Therefore, the strength of the electric field that is applied in an electrophoretic mobility experiment is typically expressed in terms of Joules per meter. Therefore, you will have units of meter inverse, that is from the numerator, and E, that is Joules per meter, which is the units in which the applied electric field is measured in electrophoretic mobility measurements. So, so now we would like to what we would like to do is to extend the concept that we have discussed about the electrophoretic mobility of the isolated ions into electrophoretic mobility of charged particles. We will do that in the next class.